Great. Okay, well, thank you very much, everyone, for coming to this bonus EEG seminar out of term. Very pleased to have with us today Patrik Jansson, who's a professor in computer science and engineering at Chalmers University, Chalmers and the University of Gothenburg, and he is a visiting fellow at Kellogg College in Oxford at the moment, being on sabbatical there this term. So we thought a good opportunity to have him come over here while he's on this landmass. So thanks very much, Patrik, for coming. Go to talk to us about optimizing sustainable energy with functional programming.
Yeah,
exciting.
Thanks. Should I?
Oh yeah. Sorry.
Okay. So optimizing sustainable energy. This is a sort of motivating picture on the left here with a sort of schematic of a fusion plasma reactor, a tokamak reactor with lots of coils with currents and so on, and then some magnetic fields and plasma inside. On the right is this, so also as sort of a test case, it's just showing the trade-off between some emissions and some spending. You want to get as low to close to the origin as possible, and I will get back to the details of that later. So, as was said before, my name is Patrik Jansson, professor of computer science, working on, well, what happened now?
Everything turned out.
I'm black just because I moved to second slide.
It could be loose contact in the
This is annoying. It did it again. I mean, it did it 1300 as well. I'm not sure. My screen, my computer seems to believe there is another screen.
Is someone also logged into the Zoom to see
it looks fine on Zoom.
What? So it is there. It's shared on Zoom, but it doesn't want to actually show.
This thing here looks very shaky.
Oh,
This is.
but that's not
not
even
going into that.
used. And this goes into underground. Wiggle.
Did this wiggle work?
Okay.
Yeah, touch it very softly.
I'd have to wiggle it.
Treat it like a tokamak.
Well, yeah. Okay. Anyway, programming languages, software correctness, algebra programming, not hardware connections. Not my specialty. Yeah, this recent collaboration I mentioned was with Professor Tunde Philip at Physics Chalmers, happens to also be my wife. We talked a little bit too much during the pandemic, so we actually ended up writing a grant proposal, which was granted, and then we had a collaboration project with some physics content, optimizing fusion using functional programming. Basically, they had simulators of some physics cases, and they wanted to optimize some parameters, and we had perhaps at least an intention to be able to do something useful with functional programming, and I think it sort of worked. I have a longer collaboration going since around 15 years or so with the Potsdam Institute on Climate Impact Research. There's been vulnerability modeling, optimal decision making, yeah, and lots of it inspired then by things in climate impact research. And I should expand a little bit, saying that climate impact research is not the same, but clearly closely related to climate research. And maybe this is simplification, but I would say from the computational perspective, climate research is about understanding the climate system by itself. Ocean currents, atmospheric dynamics, ice, radiation balance, all of these things. But the human carbon emissions or other emissions is just an input, and you compute the trajectory of the Earth system, or maybe probabilistic distribution of trajectories of the Earth system. Climate impact research, on the other hand, brings humans and their activities into the modeling. So clearly the climate affects us, but we also affect the climate, and areas that are additionally brought in is then economics, land use, policy making, and so on. And all of these things, as they involve humans, means that we have lots more uncertainty in our models. That's bad news in some sense, but it's also good news in one sense, because we don't really need to care about very precise climate models. Because if the climate model needs as an input what humans will do, and we're very uncertain about what the humans will do, then we don't need to compute very precisely the climate description. So what we do need to make these things combine together. I should also mention that we did a course where we had Anila's first seminar last spring on functional programming and climate impact research. And there was, I mean, climate impact research is a big area and has lots of specialties and so on. And this course only treats the part which we have been doing work at. So there is a sequence of papers, there's a sequence of seminars, and it discusses these papers, and there's some slides and there's some tasks to be done. And this is the list of papers that we used for the talk, for the course last year. And we're intending to run it again if there is sufficient interest this March to May. And as I mentioned before, vulnerability modeling, but also some things. I mean, I should mention this is functional programming dependent type. We've been using IDRIS, and we've been using Agda. We've been using Haskell for different things, and try to model these kinds of situations. Sequential decision problems is one core topic for like 3 or 4 of the papers, where you want to make predictions or optimize what decisions that should be made over a certain sequence of time. When you optimize some kind of reward function on the uncertainty. Anyway, that's things advertising. Back to the 2 applications that are touched on in the talk. So why do we do these parameter optimizations of simulations of fusion? Well, first of all, if fusion would work, it would be great. I mean, work here on Earth. We got the shining example behind the clouds somewhere 1 astronomical unit away. But if we could get it to work on Earth, we would have a very good energy source. And people have been working on these in more for many, many years. I mean, the Jet Torus experiment at Culham was actually shut down last year, and it's been running for 40 years, that project. And they've started a new project called spherical tokamak for energy production. But these physical experiments, and they're building ITER in France, and they're building different reactor experiments in different places. These cost billions of pounds. So this is really expensive equipment. And clearly, you don't want to be building this for 10 years, investing billions, and then you start it and it sort of blows itself up or melts down or sort of breaks in some unfortunate aspect. So they really want to model it and simulate it. So we got numerical experiments before the physical experiments or in parallel. These have many parameters, often long run times. So you really would like to have a nice cool toolkit to choose the best designs and so on. In our specific little corner together in this project, it was 2 years running. We produced a few physics paper. And I will show some results later. And then the other side, I mentioned sequential decision problems. And this picture is trying to be a schematic of that. So there's some kind of a state here, which then there are 2 decisions possible. And then here there are the 2 more decisions possible. And here it turns out there is no choice left. Maybe everything is bad and you just have to continue forward in that direction. And we try to, these kinds of diagrams are shown very often in these kinds of decision problems, and there are some probabilities in what will happen. You aim to go up or down, but you may not actually end up there because of, a pandemic or a war or things that do happen in reality. And so one of the papers that we've written reasonably recently was about exploring how uncertainty affects these things. So if you have a very simple model of the world, but then you vary only the probability that your decision will be implemented or will be effective, then you will get not even a monotone dependence on this probability. Sometimes might go up and go down. So that it's not at all, it's not automatically decidable from the beginning how to do it. And then we try to do this. Yes.
So things like alpha-beta pruning and min-maxing systems don't work because it's not a zero-sum game, is it?
No, it's yeah, I wouldn't say it's a zero-sum game, but I mean, we can certainly, so this is about decision making in a number of time steps in a system where you assume that you know the transition probabilities,
Right.
and you know some measure of the rewards. And then you can compute with backwards induction from the end state what are the best decisions at every stage, which means basically the best policy to follow. And then where a policy is formally defined as a function from state to decision.
Right. So like a Q learning style problem if you apply
Maybe.
reinforcement learning to it.
Something like that.
Okay, understood.
And then the other paper here was about responsibility under uncertainty. So, for example, if you end up at this stage where you actually have only one possible decision to make, then there can't be any responsibility left. And on the other hand, somebody must have screwed up along the path to get there, because if you're in a state where you can't really choose anymore, that's not bad. So they can ask, can we compute some kind of responsibility in one of these systems? I mean, relative within the state space. So not relative to other decision problems, but within this decision problem. And then what we do is that from each state, we compute the best and the worst decision, because we can compute the sort of expected utility of all the decisions. And then if there is no difference between the best and the worst, clearly there is no responsibility left. And that can happen if there is only one choice, but also if sort of it doesn't really matter, and we can be flailing around whatever we do, but we're sort of on the downhill slope, in the ski slope, and we will just end up at the bottom. But on the other hand, if there is a big difference between taking the best and worst decision at this step and then acting optimally afterwards, then there must also be a high responsibility at that stage for doing the right thing. And that policymakers may be interested in knowing which of these steps are the more important ones and spend more efforts in exploring the details of those decisions. Anyway, so these are two very different areas, the fusion side and the climate impact side, but they have some things in common. Real experiments are either very expensive in the fusion case, or basically impossible. I mean, if you want to explore different taxation schemes for carbon emissions, you can sort of, let's select 2 random European countries, implement 2 schemes, wait 10 years, see which worked, and go back in time and implement the better one for everyone. It doesn't work that way. We don't have a planet B to experiment with and so on. And that clearly means that it's important to do computer simulations. It's also, which is not the topic of this talk, but it's really important that the computer simulation is actually doing what you think it does. So you don't sort of decide on the future climate goals based on numerical errors or algorithmic errors and so on. So in many cases, you have several input parameters, and you have also several what I call objectives. So in this sense, I will just talk about objectives as that number coming out of a simulation. So it's something we want to minimize. It could be, in the fusion case, stresses on the wall, the heat load on the wall, the currents that are running, things that you want to keep low to not destroy the experiment. In the climate case, the spending for doing some climate intervention, the emissions, perhaps unemployment, these kinds of things you want to minimize. And I'm sure you can make up your own favorite topic here, where multi-objective optimization is important. You want to buy something which is both good and cheap, things like that. So if we go a little more mathematical, we want to do multi-objective optimization of a black box function. And I will expand a little bit on this. So here I will assume that we have a function f from m real numbers to n real numbers. I should say, from a computer science point of view, there is nothing special with real numbers here, and we actually don't implement real numbers, as nobody does, because that would be very inconvenient. We implement floating point numbers, and from the theoretical point of view, it would be nice to have different types with different orders, because sometimes you may want to compute an integer or something like that. But that's to make this work out with a few people in physics and so on, we basically have to talk about real numbers. So m parameters in, n objectives come out, and then we want to find approximate minima of f. And then I will just expand on the different words here. So expensive here means that each call to the function can take minutes or hours to evaluate. So we don't want to just make a dense grid over all possible inputs, 1 million calls, and then wait for 2 years until it finishes. Black box means that we can only learn about F from calling it. And I should say that this, you say, oh, but we might have open source software here. But if you have open source software of a simulator of a physical system, you will not look at the source code and say, oh, but then I know the inputs, which will give a nice, smooth fusion experiment. I mean, of course, you can see of the source codes what it's supposed to implement equation-wise, but you can't really see the output. So black box here is, even if you know the source code, you don't really know the behavior of the function before you run it. And if it's expensive to run, that means that, yeah, it will take a while. Objective, as I mentioned, something we want to minimize. There are n of those in this setting here. Function, this is interesting. I had to add this. I didn't have it in the previous version of the talk, but then I realized that function is used very loosely in very many fields. Like climate change is a function of our behavior. Well, in the sense of sort of natural language, and that it depends on our behavior, yes. But it's not a function in the mathematical sense that if you change only our behavior, then we will know, compute what the result is. So I mean, you really, here I'm just talking about basically pure functions in a functional programming way. If you call the simulator twice, you will get the same output. And that is a restriction. Of course, there are lots of places where you use randomness in your computations. And this particular line of work does not cover randomness. Bayesian optimization would cover it, but we will not use it here. Or, I mean, we will not depend on that here. But it does mean that we can, for example, memorize things. If we have run it once, we can keep that result in the database, so we don't have to spend a few hours computing the same input again. And then finally, approximate minima. Well, we are actually looking for inputs, the parameters, for which we get reasonably small objective values. And I'm a bit vague on reasonably small here. And partly that's because it's a multi-objective optimization problem. So there will be usually a trade-off between the objectives. You can't sort of say we will get the minimum objective 1 or the minimum objective 2. We want this trade-off function. In the physics example, which will show some results from later, we have sort of decided on all the other parameters and we're varying 2 of them. And we have also 4 objectives in that setting. And that's a little bit annoying. It's very difficult to visualize. So in that setting, we actually did use a cost function to sort of combine these together, and we'll get back to that. And the interesting thing, which is not really part of the talk, but it's a bit fun, that what we do in this particular experiment we did for this 2 physics paper is about trying to turn the reactor off. So cool it down when some anomaly happens in a reasonably fast way. And the problem is we have like a mega ampere running in these coils and so on. So if you just sort of turn it off like that, there will be rather big forces on the actual infrastructure, and bad things might happen. You get all the current is usually, well, so a large portion of the current ends up as something called the runaway current. So it sort of becomes a beam that penetrates the wall. I should say it's not dangerous for anyone else, but you have a high vacuum in these things. And then it's 1,000,000 degrees inside, and then you have superconducting magnets on the outside. So if you drill a hole, 1, you haven't got a vacuum anymore, and 2, the cooling medium will leak in, and it will be very messy to clean up. So you really don't want this thing. But it's only a few grams of fuel, so it will not cause a nuclear breakdown or something like that. Just I've been told I need to mention this because people are afraid of nuclear stuff. So this is nuclear stuff in the sense of fusion, but it is a very other end of the spectrum than the sort of fission nuclear stuff. Okay, that was the physics example. I will also show some images from a sort of made-up example based on the climate case. So we have done a number of things in the climate side, but not with multiple objectives yet. So we'll have a made-up case there just to show how these things depend. And there, it's about choosing how to act year 1 and year 2, maybe how much to invest year 1 and year 2, and then computing what the emissions and the spending are. In all of these cases, we want to minimize. And of course, if you would like to maximize, you can just insert a minus sign somewhere. Okay, so there is rarely a single input which minimizes several objectives. So you have this trade-off, you know, if you want to buy something, if you want it cheap, you might have to compromise on the quality and the opposite. So this is the same case here. And a very common way of handling this is to say, well, okay, let's trade off these against each other with a cost function. So you measure the different objectives, you decide for some prices, and so that there's basically weights, and then you sum them up, and then you optimize a single objective problem, which is the price, the cost. And I will look at this now for a few slides, and then get back to the true case later. Yeah, I think I mentioned that already. We've published 2 papers on this, cooling down the reactor. I think one of the slogans used in that talk was you throw snowballs at the sun, because you inject a combination of deuterium and neon gas, but you've frozen it to pellets. So be able to accelerate it and shoot it into the plasma. So you're actually throwing snowballs at the mini-sun. It's a sort of funny case. And the reason you do it in that way is because if you want to get it inside the plasma, it has to have a bit of inertia. If you just puff the gas, it will not actually go in, it just will be staying around the edge. So you want to go in and then melt and be in the middle. Yeah, and I would just illustrate here. We did Bayesian optimization with the cost function. And these next few slides, I'm sure everyone has seen some slides on Bayesian optimization before. The reasoning I'm showing it here is mainly to sort of get this concept of the black box function through. So this is a typical example. The blue thing is the thing we don't know. There is some function, it's of one parameter. It very much looks like the sine function or yeah. But let's say we don't know that, and we start with some very little knowledge saying, okay, the result will be around 0, so that's the dashed line, and we have some confidence interval, so that's the sort of reddish part here. This is at 0 evaluations, nothing is known, that's really the black box. We make one evaluation, and suddenly we know exactly the function value at this point, which happens to be accidentally almost the maximum, but we're looking for the minimum anyway. There is very little uncertainty. I should point here so it's visible also on Zoom. But then the uncertainty grows. So over here, you don't really know anything about the function anymore. Well, except for the now we're updated. So this is still the same confidence interval width, but now we know it's sort of between -1 and +3, or we believe it is. That's our updated knowledge about the function. And then if you evaluate a few more times, you will get a closer and closer uncertainty regime around the true function. And we also have to be careful on balancing here the exploitation and exploration. Exploitation means using really the knowledge, and exploration means searching broadly, because with the partial knowledge we have, we may lose sort of certain areas. I mean, we know very little about over here, so we really have to do some evaluations here, even though we're pretty sure on the value at these little regions. And I will not move on very long here, but this is sort of after 7-point evaluations here. These values have, well, at least made the dashed line resemble the blue line, you know, the ground truth that we actually do not know. And we have an estimate not only of the function, but also of the uncertainty remaining. I should mention that if the function would be a very evil function, say, you know, these things that end up in calculus textbooks, it's 1 on all the rationals and it's 0 on the irrationals. Clearly, there wouldn't be any hope of ever recovering that function. So we have to make assumptions. For example, here it's not only that it's a smooth function, but also that it has basically a maximum derivative, because you saw the growth of the uncertainty had a certain slope. So that basically tells us that we can't jump too far in a small space. And that part we will also carry over to the other example. Okay, now for some results on the physics side. First, this is just a slide on the simulator. So the black box is the dream. It's disruption runaway electron analysis model. It's a simulator. It has lots of parameters. It computes heaps of values in space and time and phase space and so on. And then it computes from these four main objectives which are used in the optimization. And it's some current and some time and some eta, but they are sort of proxies for safety of the device. So you don't want the current too high in the runaway currents that might enter in the wall. You don't want the time to be too small, actually, so that we will have another sign there because of this induction effect. When the current shrinks very, very quickly, you will get such physical forces on the magnets that it will break the vessel. And this eta count has to do with the radiation pressure on the wall, so you don't want the wall to melt. I mean, it's 1 million degrees in the middle, and if you cool it down too quickly, the heat will end up at the wall, and the wall, even though it's from Wolfram or something like that, it will still melt. So you want to keep these different values down. So a few things then about the cost function. So first, note that it combines values of different physical dimensions. It combines currents and times, etc. So clearly, you can't just add them up. It wouldn't make sense to add one current and one time and one, I don't know, third unit. So we need to do something to handle the dimensions here. And what's usually done, or I should say, they're also usually of different orders of magnitude. I mean, for example, in this case, we're dealing with megaamperes, but with milliseconds. So clearly, you want the time should have some importance. So, but then there are usually threshold values that we can get from the sort of experts. And then if we divide the input by the threshold value, then we'll get something of order unity and also dimensionless. And that helps us to be able to, the next stage, well, look at as useful numbers that we can sort of combine. This is just really, I wrote recently a paper which is still under review on types and dimension analysis and so on. That's fun stuff. There's been work done on dimension analysis a long time ago, and you've also published stuff here. And there's a tool I heard for Fortran for doing useful things. Yeah. Anyway, when you have done that, when you normalize them so that there's sort of order unity, there is some kind of a border, you want to keep the values down, then it's a question, how do you combine them? And for example, you can take the maximum of the absolute value of the different inputs. And that has the good thing that it's sort of an and. So you have to be below, below, below. All of them have to be below at once. And it's sort of illustrated by this figure on the right here. The blue box is the safe box when all the three parameters are below their limits. And the red surface is the sort of point where this measure would be 1. But it's actually not a very good one for most optimization methods, because optimization methods like gradient descent want the gradient to be informative. And if you take the maximum, that means that exactly one of the inputs will be sort of active at once, the biggest one. And if you take the partial derivative of this function, it will only always have a slope 0 in all dimensions and 1 in one dimension. So it doesn't really guide you towards the origin in a very useful way. Only when you sort of cross the boundaries of some other parameters become the maximum, then you will sort of get a completely different direction. So it will be a bit erratic. So therefore, very often you do the 2 norm or the p norm to some other p. And it's just, these figures are just illustrating that the box here, which is the infinity norm, here is the 4 case, the 2 case, and the 1 case. And the blue box is the sort of safe region. And then you have this surface which approximates the blue box. I thought it was an interesting illustration. Okay, so what are the outputs from the physics experiment? So in this particular case, some Bayesian optimization with this cost function was run, and all the blue is sort of, well, the little blue we have is sort of good, reasonably good, and all the red is bad. So what do we show here? Well, we show the concentration or the amount, the number of deuterium particles, the atoms, and the number of neon atoms that are being put together in one of these little pellets, which is frozen and shot into one of the snowballs. I should mention the gray dots, if they're even visible, the little gray dots here and there. they are the point evaluations done. So this particular case is after, I think it was 250 evaluations, something like that. And they are a little more densely populated in this blue area than elsewhere. So there is a certain, the Bayesian optimization will choose points which tend towards the optimum. But I should note that this is still the optimum of the cost function. We don't know from this diagram alone what happened with the different objectives. And one sad thing to note is the blue scale here ends at 10 to the power of 1. And remember, I said we had set a threshold for each of the parameters, so 1 would be safe. So 10 here, which is the best we can find, is actually still not safe. So in this particular case, what we can tell the physics people is like, well, this looks bad. We need to change somewhere else some parameters so we can get actually even better results, because here, at least one of these objectives is actually above this threshold. Because yes.
And can you distinguish between a badly formed discrete function versus incomplete knowledge here? So if the actual function you're looking for in the black box is a badly formed function.
What do you mean? If it's like discontinuous?
If it's discontinuous or it's got some property there. You don't really know anything about this.
Well, I mean, what we can do is we can look at the partial derivatives, the approximate partial derivative between the points. And if when we get closer, the difference is the same, right, which means the partial derivative increases, then it very much looks like there's
some jump somewhere.
A jump there, yes.
Right.
So yes, we can sort of, I mean, the Bayesian optimizer will not tell you, but we can look at the data we get out and we can sort of search for these kinds of cases.
Got it.
I should mention related to that the function is actually discontinuous in the sense that most of these runs are runs which end at the simulator saying raised some exception, because it has assumptions and so on, and sometimes it will just realize that I can't do this, or it's not within my regime, so we will just sort of crash out. And then it's actually not an obvious choice then what value to give to the cost function in the exception case. Because if you set it to say 0, that would be very bad, because that would be considered the best. And the optimizer would just say, oh, I'm done. We raised an exception, we got the cost 0 here. If you set it to 1 billion or something like that, then the Bayesian optimizer will be so afraid of this point that it might miss nearby points, which are still good. So you want to put a bad value as the output of fails, but you don't want it to be significantly worse than any other bad value. So it's actually one of the things I don't have a good solution for. So we sort of experiment there a bit. Anyway, I should say blue is good, red is bad. And yeah, one optimum is at the start, but we really want to know the full trade-off curve and to explore a little bit closer. And I will get back to that at the end of the talk. So then let's look at the alternative 2, multiple optima, and the trade-offs. And first, this will be a few slides just explaining what the Pareto-front is. And as the lead into that, as I've mentioned, there are basically relative weights on the different objectives in this case. The weights, I motivated them by dividing the values by thresholds, but you can see it as multiplying by different values just to get them on the same size. But anyway, these weights will be in some way setting prices for different bad things that can happen. So you can say that the cost function is called a cost function because it's basically some kind of measure of a cost. And the way you set these weights can significantly affect the optimum without changing the physical world or the model. So that's a bit strange. You say, you call one of these optimizers, you find the optimum, and then it says, oh, why, anyway, if you change the weights, you get another optimum. And how can one be an optimum and the other as well? So you have to choose the weights, and it's not only a mathematical problem choosing these weights. It could also be a legal or ethical problem. So for example, the most concrete, if one is measurement of expected lives lost and the other is a cost, then the cost function will give you a price per life. And if you're a company, then the lawyers probably say, no, you cannot set a price on the life. That's sort of, I mean, in practice, you can probably read it off from their engineering guidelines. but you cannot in any written document or any source code say that, oh, well, a life, that's 100,000 pounds or whatever. So that would be very difficult. So there are, in addition to the technical reasons for keeping track of the real trade-off, there are also sometimes legal or ethical reasons for it. Anyway, the Pareto-front is the trade-off curve, and we will get to that very soon. So now I move, because it's difficult with this real case, the physics case, to understand what's going on. So I just made up a case, and the case here is inspired by the climate side and this sequential decision problem. So year 1 and year 2, and you can control this by some parameters. This is the rectangle you're given, and then you have to find some optima in this rectangle. The function that we talked about many slides ago, that's the function f. On the right side is some spending and some emissions, and just to avoid strange questions, this is relative spending and relative emissions to some base case. So it could very well be negative actually, but we focus on the positive side here. So you want to minimize spending, but zero spending will not mean that it's completely free to avoid emissions. And zero here on emissions is also not completely free. But to start out with, it's a black box function. We know nothing. We have no points on the right-hand side. And ideally, mathematically, what you would do, you would take this set of points, this infinite set of points, you would just map it through the function, and you would get a set of points on the right. Maybe say covering, I mean, typically there's a trade-off curve here, and maybe covering this upper side here. What we can do instead, we'll just have to start with value somewhere. So little a maps to capital A. And still, we can't really tell the policymaker anything useful. We have to evaluate at least one more point. So here we now have a point B. We'll just sit slightly so I can point to them. So B is clearly better than A because it has a slightly lower emission count and a significantly lower spending. So it's improving in both objectives. So there's no point in using point A. Okay, well, we could report to the policymaker B is good, but then we want to know a little more. So we evaluate one more point, which happens to end up here. Now this one has slightly less spending than A and significantly smaller emissions than A. So both B and C are clearly preferable to A, but it's not clear how to compare them internally. So we don't have a total order on these points. So they are, depending on who the stakeholder is, they may have different opinions on emission and spending, or also depending on the scales. I mean, it's the megatons of emissions and the pounds of spending. So 2 pounds, we can spend 2 pounds. That's fine for reducing the emissions with megatons, but maybe not if it's the opposite. If it's tons of emissions and mega pounds of spending and so on. Anyway, evaluating a few more points. Now, D here is better than A as well, but also not obvious which is better. You might say, well, D is better than B and C because it's actually diagonally closer to the origin. It's square root of 2 instead of 2 units away from the origin. But again, it depends on your weights here, on your perspective. It's not at all obvious that emissions and spending are on the same scale, even after you divide by sort of some threshold value. And just to show that here we picked a point in the middle of these, but that point actually ends up outside of this rectangle. So these are always non-linear functions. And this particular case, E happens to be better than D. So here we got 3 points, B, E, and C, which are all sort of different kinds of compromises between the objectives. And we have D and A, which are clearly inferior to, well, at least D is inferior to E and A is inferior to all of them. Okay, so summing up here, now this is about showing the blue curve, which was the sine function in the previous case. Here I filled in with infinite computing resources in theory, exactly what this shape is. And what you see here, the sort of kind of, this is the coordinate grid in the input space, which has been warped through the nonlinear function and ended up being this kind of, you can imagine it's some kind of net. And you can see here that the trade-off, well, I should be showing here, the trade-off curve is following this end of all these lines. So if you these curves are constant year 1 or constant year 2 curves. So you can get from D to C, for example, it turns out, by changing only one of the parameters. And then you can change the other parameter to get from D to B, and so on. And yeah, I would say policymaker-wise, E is probably a good compromise, but it's not obvious which of these you should report. And to sum up, I would say you want to present the Pareto-front to the policymaker, or at least a few alternatives, like here B, E, and C. Like, okay, these are choices you can make, and this will give different trade-offs of the different objectives. Okay, so how do we compute this in reality? I mean, we don't randomly just pick a few points. So remember I said we started with a rectangle in the input space, or a I don't know what it's called, hyper rectangle, perhaps. And then we evaluate at those 4 points, and then we choose to split either in one or the other direction. You could say that we could always split in both, and that is also working, but if you got several objectives, it becomes a rather broad recursion, sort of. It splits into very many cells at once. And also it's the case that rather often the physics or the sort of climate science of the thing may depend much more on one of the dimensions than the other. So if it varies very slowly in one dimension, then we can subdivide the other dimension until they vary roughly the same speed. Anyway, we split, and we try to use heuristics for which cells to split depending on the current approximation of the Pareto-front. And this was the slide I had before. I've just added this time to zoom in and added a rectangle over there, which is very thin. So what we did was we started with this case with a full square, and then we let the this sort of adaptive mesh refinement like algorithm search. And on the next slide, I will just show this thin rectangle, but as squares. So notice here is now 21.9, 22.1. So that's the thin dimension, which has been sort of expanded. And the other one is, well, it's not a full square, but it's almost a full square on the other direction. And what do we see here? Well, now I want to do without the cost function. So this is one of the objectives, this is another objective. So there are actually 4 of them, but I show the 2 most important here. It's not very easy to see, but blue is good, red is bad. So this objective, you want to avoid this part and you want to go toward this corner. This other one is just the opposite. This is the bad part, and this is the good part. So that shows really that there is a trade-off. And now we've tried different ways of visualizing, but here the color of the points along the Pareto-front, which is along here, this is now showing the objective space. This is just showing a measure of the current. This is actually the 10 logarithm of the current after the threshold value. So the current is fine here. It's like 10 to the power of -3 of the threshold and so on. And it shows how that trades off with this time term, which is in this case, it actually has an interval, so it's a little more complicated. But anyway, it's a number which we want to minimize. And the nice thing is that you can see, or at least those who know the physics can see them, which are these points? Well, there was up here, and which are these points? Well, there's actually 2 groups of points here. Notice that this is a nonlinear function. There could be any number of islands in the input space which map to the Pareto-front. It could be sort of good areas in different places. There is no connectedness requirements here because it's just the inverse image or something. And it's interesting from sort of geographic, it looks like there is a curve here, and then this is a little like a bit of a different thing. So I think this part is one of these blobs. I haven't dug down too much into it. I should also mention one last thing about this, and this is the strange line going out here. So it's not visible on this diagram, but we actually have added arrows from each point on the Pareto-front to its nearest neighbors. So here you might notice there are dots. And here, for example, is a rather big rectangle, which hasn't been split so much. Here, it's got tiny little rectangles. So, but anywhere we are on the front, we take the value at the next 4 corners, up and right and left or down, and we put some more arrows to them. Most of those arrows are not even visible. But here, which is somewhere here, the neighbor is actually far outside the box. So it means that even though this is just as other points on the Pareto-front, you probably don't want to use it for the experiment because it's a very sensitive point, which means that given that you cannot implement the physics exactly as the model, means that you may very well be just next to it, which means elsewhere.
Right.
So it's something I haven't talked about here, but robustness of the results is also important. So that's yet another thing we would like to measure, and that's attempted measuring it is little arrows here and there. When we only had, this was 600 points, after 200 point evaluations, the arrows were more like pointing in all kinds of directions. Okay, some lessons learned. We memorize the results from the objective function, and that's to avoid recomputation because it takes time and it's nice. I didn't think that was a big deal, but it turns out that my wife is working with the students at the other side. I mean, they wished they had saved the results, but apparently they hadn't because, you know, they sent some paper in, they got review results, and then the reviewers wanted something, and then they said, oh yeah, we will have to run it over again. We have to wait until after the weekend because it will take 72 hours for the simulation to be done again. And so it's nice from sort of being able to act quickly, but also, of course, for us, when we evaluate the algorithm for finding the Pareto-front, to be able to run exactly the same thing again in a second, instead of waiting 24 hours for all the runs. It is a little tricky to keep track of software versions, because there is always a tendency, we do something and then say, oh, but we will change this in the simulator in Dream. And then we say, well, we will not update to the next Git commit of this until we've done all the simulations, because we don't want our simulator to change under our feet. We really want a pure function here. We don't want suddenly some other function on. Anyway, correctness guarantees. This is related to the fact that we were running Bayesian optimization first, and I wasn't very happy with the output because we minimized something. It said, okay, this is the minimum. And then we did some sanity check. We made a thin rectangle around the minimum and ran it again. And then I said, oh, by the way, this is an optimum which is 10 times better. So, I mean, it will stop at some point, the Bayesian optimizer, which is for us just another black box. And now when we did it our own way with the adaptive refinement, we wanted to keep track of the errors. So basically, we asked the user for the bounds on the partial derivatives of the objective function. And then that means that in each rectangle, we know the uncertainty left. We sort of have an uncertainty budget that sort of shrinks down. It's a bit interesting what happens when the assumptions are falsified, as what you mentioned there. If there is actually a big jump somewhere, or I mean, a discontinuity anywhere, then it will be falsified after a while. And then we will have to either adjust the partial derivative. But that is also good that we have saved the values of the function so that we can run it again very quickly with another assumption of the maximum derivative and see without having to recompute lots of things. And then, as usual, there's a difficult trade-off between exploration and exploitation. So on the way to computing the Pareto-front, we will have actually from the first point evaluation of function, we will have approximate Pareto-front, which is that point. And then you have 2 points. There might be 1 or 2 of them on the Pareto-front, depending on one dominates the other or not. But those first, say, 50 or so iterations, the Pareto-front will be a very coarse approximation of the reality. So we will have to explore also points which do not immediately lie near the Pareto-front, but it's not obvious how to do that. So that's still work in progress, and I should finish a draft paper. Okay, and that's a summary then. I mean, we did some examples on fusion energy, climate impact research. Part 1 talked about Bayesian optimization and the cost function, and then this Pareto-front computation. And yeah, I mentioned this FP climate course, and that we're still trying to write a paper about the Pareto-front computation, and we will want to do applications on optimal climate decisions. We're currently a bit in the lack of funding for employing somebody to do it. So we applied for funding several times and got them all rejected. But yeah, that's the current state. Questions? Yeah.
So thanks very much, Patrick. Can you say a bit more then about the functional programming side? Like,
Yeah.
What language, what techniques, what was the
Mhm.
kind of the benefit from doing this with FP rather than writing some C code or something?
Yeah. So I mean, this is written in Haskell. I mean, what we did was written in Haskell. Of course, we haven't touched Dream. The Dream is this simulator which has a Python front end and a C++ core, and there's lots, like a few man years of work that has gone in there. So Haskell hasn't been, I mean, has been good for rapid prototyping. It's been good for quick checking different properties and so on. I think that our feeling that we like lazy evaluation was key to implementing this memoization like very early on. I mean, the memoization here is a hack. I mean, when we call the function, we have a layer on top. I mean, calling the function, as I mentioned, this is a black box, and we actually call it by a shell. So we really call the binary on disk. But so the function which does this is in Haskell looks like a function, but it actually has the side effect of saving the results of this on disk and doing a hash sort of the input, so it can sort of retrieve it later and check if it's been evaluated earlier. But I think well, implementing in Haskell has been, I think, a good experience, but most of the work on the Haskell implementation was done by 2 or 3 master's students in parallel with their studies, because we had a rather limited budget for this project, and they have left, and we have the code. And it's not true that Haskell code is always eminently readable. So we have a little bit of a challenge in, so, okay, should we just throw it out and redo it? Because now we know what it does and we can do it sort of in a more structured way, or should we sort of gradually refine it and so on? But of course, it's good for me that it's in Haskell and I can sort of access it. I mean, I should say computational speed here is not an issue because the time is taken by the simulator. So
right.
That should, yeah.
Really enjoyable. So you're making a bunch of decisions with the memoization about when to store stuff on disk and when also when it's useful and when you're using it. So can you just apply your Pareto-frontier technique to figure out when you should memorize the things you're trying to find the Pareto-frontier for?
Well, so strictly speaking, we only would need to save basically 4 real numbers for each point, which would be the sort of the 4 objectives in this particular case.
Yeah.
But we save more because when we say that something is strange here, the physics people want to look at the output.
Exactly. Yeah.
And then there are some parameters to Dream. To what degree you should save stuff, and if you say, oh well, let's just save everything, then you get 4 gigabytes of data per run, which is not convenient.
No.
So we sort of have some intermediate setting there, and I think.
But fundamentally, though, you're trying to do a trade-off between the utility of memoization versus the cost of memoization, right?
Yeah.
And we have similar things with disk usage and how to store intermediate data, and then is the result of this thing actually being used by something else in a dependency graph? It does seem like
so currently, no, I mean, as I said, we could just store these four numbers per run, or a few more because we store the input parameters as well. So, but yeah, that's a very, very small thing, which would not be a trade-off thing. But so far we've kept some intermediate setting of the data desk because we want to interact with the physics people. It's easier to say that we can sort of draw. Yeah. They ask not what the maximum current is. They want to know the time evolution of the current. And why on earth did you get such a low maximum current?
So you're building this for users, right? So like the intermediate stuff is part of the input and output as well. And also,
yeah, I guess.
Like if you're trying to decide between like all the intermediate, like if you're trying to figure out the partial derivatives in order to find discontinuous functions, you'll need more than just the 4 outputs, wouldn't you? You'd need the intermediate results in order to figure out what's going on. So it feels like the memoization is bigger. It's a big simulator. So,
well, I mean, the partial derivative is just a difference quotient. So if you have the 4 values there and the 4 values at the neighboring cell, you just.
Oh, you don't need any intermediate results.
No, I mean we don't have intermediate results, so to speak. I mean, we only have the output that we run the simulator on. Actually, the interesting aspect is now we've sort of been running this in lots of different parameters, the algorithm to find the Pareto-front. We actually have accumulated quite a database of runs,
Right.
which are not exactly the same points. So now we can choose, we sort of have a better answer than what we get from one computation. We can look at what the other ones did. So we have a denser sort of point cloud in reality, even though it's very sort of unevenly explored, because it always ends up roughly the same, except for the cases when it sort of runs off in a corner and splits and splits and splits and splits in a corner, which has happened a few times. Yeah, I haven't thought too much about how much to save, but yeah, disk space is a bit annoying. It's not costly per se, but we don't want to put it in Git, for example.
It's got to be managed, right? Yeah.
Yes.
I'm interested in your assumption that F is deterministic. Because it seems like a lot of functions will not be. I don't actually know, but my prior is that a lot of functions won't be deterministic.
Yeah.
So I wonder how this technique could be generalized to a non-deterministic setting, if you know what I mean.
Yeah, I mean, if you borrow more from the Bayesian optimization setting, I guess you can do more there, because there is just assumed that the function has a certain distribution function. So the actual simulator we run is not, I mean, it is deterministic. And even in the climate side, what things we've been running have been deterministic, but computing probability distributions.
Yeah.
So that's another sort of aspect, because as soon as you have something computing a probability distribution, of course, you could also decide just to sample it. And then you would definitely get lots of non-determinism. But the models we have explored have been very simplified climate models, but with a probability distribution as the output. So I haven't explored it. I mean, I sort of bounced back from randomness by seeing the strange results from the Bayesian optimization at the beginning, when we had these sanity checks, which never worked out. I mean, almost every case when we took the optimum and made a one-dimensional, I mean, not formally one-dimensional, but a thin rectangle and started in it, we would get a better optimum, and not by a 1%, by like a factor of 2 or something like that. And that made me want to do something with this kind of stepwise refinement of the search space and a bound on the error. I guess the bound on the error could be some probabilistic, I mean, some kind of confidence interval bound instead. But I haven't done the maths to figure out what that would look like. But yes, I do think one could go that way, to combine the things. Yeah.
Is it possible to run Dream at different resolutions as well? So you can do a sort of low fidelity search of the space by coarsening it.
Yes. So that's the part we haven't really got to, but which was part of the application that was granted that we worked on for 2 years, because there are sort of not only granularity in time and space, but there are also like 3 different dimensionality settings, or to what degree it should resolve the sort of phase space and real space at all. And those are like, when I talk about minutes or hours, it's like it takes 1 minute, it takes half an hour, or it takes 14 hours if you have one of those settings. And there is the reason and then it would be nice to do most of the search in the crudest model, which is fast, and then say if there's a factor of 10 in time, every 10th evaluation sort of do with the next level model and go down and so on. The reason we haven't got down there is because they seem to be, there are 2 reasons. One is that the inputs are not identical. So you need to fill in, when you add a dimension, you need to sort of fill in the initial state. And it's not obvious how to fill in the initial state in this physics thing. So it's not an obvious, like, to just run it at a higher resolution. And that's one. And the other is that they don't seem to agree very well. So unfortunately, I mean, we evaluate an optimum. I was saying that we really shouldn't be looking for like 3 digits optimum precision, because the model may be 10% off. Or, as it turns out, you search for a minimum, you find a point there, you evaluate it in the better model, which is more physically reliant, and it's a factor of 10 off. Because it's not because it's completely wrong, it's just because you're evaluating here or there, sort of when the world is better resolved, the whole optimum thing has sort of moved a bit in parallel to something, and then it's sort of outside of the optimum again, and that's, I think, I mean, in my head, it looks like there should be some kind of mapping between the spaces, so one should be able to say something about the translation function between the layers, but that's as far as that my head is there, but the code doesn't use it.
You could train a black box machine learning model that would
I
learn
was
that.
going to say, yeah, it would sound like a neural
Yeah.
network kind of task.
But it's small data.
Yeah, it doesn't matter though. If you have lots of synthetic data you can generate from this thing, you can do, like we've done inverted runs of agent-based models with like 100 simulations of the imperial coded simulator, for example. So you don't need a lot of data because there is a function it's trying to predict, and you
it should be so that part should be possible to learn, but I'm not quite sure about this initial condition thingy, which is a bit annoying. So there isn't and I thought it was obvious. I mean, this description I said, like every 10th run is on the next level, and every 10th run of those is on the even next level, and then it's very fine, and it will be very, very fancy. But then turns out that producing the input is not directly, well, it's not a unique function from the lower dimensional input to the higher dimensional input. So the function back, it forgets information. So when you scale to more dimensions, you have to invent those. I guess it's similar to climates and temperature and so on. You have to invent, you measure at certain places, and you have to invent temperature everywhere else. And you can invent it in different ways, and those will give different. I mean, for example, if you make it very hot between here and Oxford, then I'm sure the weather will be different tomorrow in the predictions. Yeah. Yes.
I have one question about the value that you set for like exceptions or errors.
Yeah.
Right. So you're saying that you struggle to pick the error because you don't want to set it too high or too low. But it feels like the value should be relative to the range of values that you might get, right? Because it's high or low with respect to 10 to the 1 or 10 to the 2.5.
Yes.
And so, for example, if your first run is an exception, then you don't know what to set it to because you don't know what the scale is. So I was wondering if it might be better to make that like a user decision, like the user supplies the value that.
Yeah, the user does apply it here, but I mean, we asked, okay, well, what should we do with this case? And they said, well, 10 megampere is bad, so put in 10 megaamperes there. And then we ran with that, but that was like a little too bad.
Right.
Because then it was so scared of this whole area that it will find the optimum up here or something like that. So it sort of, it had this follow-on effect. And sometimes you get, I mean, it has some interpolation function between the points. And then some, depending also what interpolation function have, if you could get a bad behavior. But yes, it's not a major thing, but I was just looking for what kinds of things can we help the users with, because they will not come and knowing these things. And then can be automated, can be, as I said, for example, after a while, after we had 100 point evaluations, well, at that point, we can probably just set it to the current maximum, or maybe actually not the maximum, but say the 90th percentile or something like that. So it shouldn't be very, very bad, but it should be bad. Because sometimes the maximum value will be just orders of magnitude worse than everything else, and you don't want that. Okay.
Right, yeah, if anyone wants to talk to Patrik more, then he's around for longer. And I think I'll park him in the fishbowl. I've got to do a meeting now, so if people want to talk to him, go down to the fishbowl or stay here and eat the rest of the food, I guess. So yeah, let's thank Patrik again.